Today I'm going to present and analyze the paper, the generation of frequency to enable shaped single microwave photons using a fixed frequency superconducting qubit that's published in a journal PRX Quantum, which categorized to the Q1 level category journal. And this paper based on the by the Muhammad and his colleagues. So before we going to deeper, I would like to give the clear definition to the key terms and ideas from this paper. First, that's the superconducting qubit. This is the quantum bit for quantum computing that uses a tiny electrical circuit made of superconducting materials which have the zero electrical resistance when cooled to near absolute zero. Next, that's a transmon is a type of superconducting charge qubit designed to have reduced sensitive to charge noise, and this is have the several levels, but only the lowest use it to the operation. They are the grounded, excited, and second excited states. And the resonator is a devices that use to store and convert electromagnetic energy at microwave frequency. And through this talk, I will refer to photons in the microwave range. These are single quanta of electromagnetic energy at gigahertz frequencies that can travel along coaxial lines that they are flying qubits for superconducting quantum networks. Let's start with the introduction. Nowadays, this rate progress of the quantum technologies that transform computation, communication, and sensing, a key ingredient in this development is the ability to generate and control individual photons. The quantum carries information that connect distance nodes in a network, while optical system can provide single photons. Using sources such as quantum dots or nonlinear processes, superconducting qubits operate in a microwave domain where photon generation poses unique challenges. This system built from Josephson junctions and operating at millikelvin temperatures from the basis of circuit quantum electrodynamics. Here, microwave photons serve as an essential link between qubits, and the models enable quantum information transfer within superconducting architecture. And they're building large quantum computers out of superconducting qubits faces a varying problems. As we added more qubits on one chip, control crosstalks became unimaginable. And one permission idea is to link smaller chip or models them microwave photons that carry quantum information between them. And there we need mention some conditions. First, conditions, and that's why controllable microwave photons matter. This is first, the sender and receiver must have the matching frequency. Even a few megahertz of mismatch prevents resonance absorption. Second, the photon must have the right temporal shape so the receiver can absorb it with near unit efficiency. The perfect case is a time symmetric waveform because the receiver absorption process is a time receive of the emitted decay. And therefore, the ability to shape the twin microwave photons on demand is essential for linking distance qubit and building scalable modular quantum computers and quantum networks. And the traditionally solution, they use the flux to enable qubits or couples where they have some kind of limitations. The limitation, you can see they're mentioned as a first, that's increased sensitive to magnetic noise. decrease in coherence. Second, that's additional control lines that generate heat in a cryogenic environment. And the last limitation, that's greater fabrication complexity limitation scalability. And the key question of this paper ask is, can we obtain tunability and waveform control using only microwave devices without adding flux hardware? Because traditionally they use flux tunable and the control using only this. So the outcome these issues, Miyamura and the other afters uh, researchers introduced a new approach based on an off-resonance driving of fixed frequency qubits. In this method, the emitted photons frequency and temporal profile controlled entered by the uh, properties of the applied microwave drive its frequency, amplitude, and phase, while the qubit itself remain fixed and stable. How you see in this figure, it's the schematic of the system that introduced Miyamura in this paper. So this is the in this work, they demonstrate the hardware-efficient approach to generate frequency-tunable shaped microwave photons using a fixed frequency circuit, whereas superconducting qubit is dispersively coupled to a resonator. So next, that's to let's move on the theoretical background. So the theoretical basis of the studies is circuit quantum electrodynamics, which models the interact between a superconducting qubit and microwave resonator. The qubit acts as an artificial atom with decreased energy levels. There shows the energy levels. G has mentioned the ground that's excited, and this is the second excited level. When coupled to the resonator, these levels exchange energy in the form of photons. And normally energy levels, the qubit and enter the resonator produce a photon at the resonator's own frequency. However, if we drive the qubit with a microwave tone, whose frequency is slightly determined from its transition, something interesting happened. Of resonant uh, and to go before this, a central theoretical advance of this work is to use of an off resonant microwave drive to control photon frequency of resonant driving means the control field's frequency isn't exactly equal the qubit's transition frequency. This drives mix at the qubit state and creates what we call dressed states, hybrid states of the qubit plus the microwave fields. And instead of driving the qubit exactly at resonance, the drive frequency is determined by a small offset. And this changes the energy um, of conduct to this equation with the frequency. This shows the exactly uh, in this off-resonant driving regime, the system must satisfy the energy conservation relative of is the transition frequency between the graduate state and the excited state. So this is the drive frequency omega, the and the omega here in the second side of the equation p h emitted photon frequency. Therefore, the photon's frequency can be turned by changing the turning of drive signal, and the resonator acts as a Lorentzian spectral filter, shaping the emission rate. This is the gamma is a formula for the emission rate, where the kappa is the resonator line width, basically how quickly energy leaks out, and the GF, there is effective coupling between the qubit and the resonator under the drive. This polarization depends shows that the resonator acts as a spectral filter. Emission is strongest near omega and weaker away from resonance. By adjusting the drive amplitude, the determining we can tune both of them and the center frequency of the emitted photon. So uh, in the short that the resonator decided which the frequencies can escape, and the drive decide how much and how fast energies is limited. And let's go to the drive device parameter of this experiment. Before um, going to set up, here you can see the schematic of the experimental devices. This device consists uh, like divided by color, and each color means the name of the device. So the green one, this is the fixed frequency transmon, and the connect this connected to the blue one, coupled to a fixed frequency resonator. This is the blue, and the circuit incorporates an instincts Purcell filter is a resonator and has an additional band pass Purcell filter. This is the orange, and the which coupled to a waveguide. This is the purple, and the red one. This is the qubit is driving via the dedicated drive lines. The experiment used a fixed frequency transmon. How we mentioned this is a green and qubit on a surface substance capacitive capacitively coupled to there are two resonators, the one for the photon emission and the one for the calibration, and the qubit made for aluminum Josephson junction has its frequency set by just geometric elementation, the need for flux tuning circuits. And there are the qubit main transition frequency is about 8 gigahertz, and the resistors is around 10.3 gigahertz with a line width kappa which equals to the 2p divided 53 megahertz. A large kappa gives us a wide emission bandwidth that's great for tunability, but it's usually causes fast unwanted decay of the qubit, a problem called the Purcell effect. So that's why there we have the circuit included a Purcell filter that blocks spontaneous emissions while keeping the resonator uh, wideband. The qubit lifetime is the stays around 28 microseconds, long enough for perceived control. And all experiments that's research performed in a dualation refrigerator at around 10 microkelvins to ensure superconductivity and suppress thermal noise with the same mounted in a gold planted copper package for electromagnetic shielding, and the input line heavily um, attenuated at multiple stage. Micropulses are generated by arbitrary waveform generated and shaped in amplitude and phase via an IQ mixer. There are IQ mixer means not about the intelligence. This is the I means in phase and the Q is quadratic, which means this their signal types. So that's signal type. So the emitted signal passes through cryogenic circulator and the Josephson parametric amplifier with 20 decibel gain and 10 of megahertz bandwidth followed by future amplification and at 4 Kelvin and room temperature, down conversion, and digitalization. This setup enabled direct measurement of field quadratics and a full reconstruction of Faraday waveform with calibration returns correction for mixed imbalance, cable decay, and amplifier gain. Mm, so that's the all characteristics of the devices and experimental setup. Next, we before performing wave shaping, the afters firstly characterized how emission depends on the drive parameters. So the preparate the qubit in the second excited state and the applied square microwave pulses with different amplitude and the deterrence at the decay rate for each drive. Plotting gamma, there is the emission rate. This is frequency give Lorentzian uh, curves centered near the resonator's frequency, just as the theory predicted. This confirmed that the resonator truly behaves as a spectral filter. The important result of this step is an empirical map that later uses in the designing of the tools for engineering specific pattern shapes. So um, you can think that as collaboration before creativity, first they learned the system response, then they use the response to sculpt the pattern, and the conform the resonator acts as a spectral filter there. And this is the formula that gives for the emission rate that's characterized. So uh, it's worth uh, then the resonator links the energy with the transmission lines at the kappa. Also here, I want to tell about the graph, the figure, how you see there are uh, that in this axis there are photon emission rate, and in this axis is a photon frequency, shows that the exacted photons emission gate as a function of the emitted photon frequency. The rate exhibited uh, Lorentzian like depends certated at the resonator frequency with a width corresponding to the resonator line width observed. And as they demonstrate, they give the different there are amplitudes, variation drive amplitudes. So the colors means the different amplitude of the amplitude of the drive voltage that they give. And the next, that's the temporal photon shaping and efficiency. Hmm. Now, this is, we can say, the heart of the experiment. Using the calibration data, the afters numerically designed amplitude and the phase modulate drive pulses that yield a specific time depending emission rate, and their target waveform was a symmetric hyperbolic scan pulse, and because such a shape can be perfectly reobserved by a time reversed receiver. And the drive amplitude controls the instantaneous emission rate, while the drive frequency is adjusted to cancel the sharp shift uh, included drift. This combination allows them to create arbitrary pattern shapes while remaining in the adiabatic regime, where the resonator follows the drive smoothly. And that the authors quantify shaping efficiency by integrating the mentioned Farad intensity over time and comparing it with the expected single photon energy. So the measurement efficiency exceeded the 19%, showing that nearly all the qubits excitation energy was successfully conserved into a propagating photon. That means almost all the qubits excitation energy became a traveling photons. Very little was lost inside the resonator. So at this point, they have photons whose frequency and temporal envelope are both programmable, created and entered by electronic control of a fixed frequency qubit. And however, the result was good, but the team noticed that when they shaped photon this way, the emitted field sometimes had a drifting phase. Its real and imaginary components weren't symmetrical. If you look this the figure in a graph, firstly they give without correction. How you see the target is a black pointing, and the reality was the orange all, and the orange pointed is imaginary. They was so different before um, uh, weren't symmetric. So this phase distortion arises because the stark shift depends on drive amplitude. As the amplitude changes, the qubit's energy levels shift slightly, giving the emitted fields a slowly varying phase. The correct is they measured the phase of the emitted waveform and then prepared the opposite phase to the drive pulse. And this technique is called digital phase correction. That after correction, the photons imaginary components nearly vanished and the waveform becomes perfectly symmetric in time. How you see after the phase correction, the target and the reality was the similar because and this is the important because the efficiency of photon absorption in a receiver depends on mood matching. Any underwanted phase drift breaks the symmetry and allows the probability that the receivers capture the photons completely. So phase correction is not a cosmetic improvement, is essential for quantum network performance. And after all this establishing, they make the verification part. That's the quantum state tomography. This is the method to reconstruct the full quantum state, its amplitude and phase by measuring many observation. In optics, it's like pick and multiply shadows imagined to reconstruct at 3D objects. 3D objects. So the team of the research verified the quantum nature of the generated photons using quantum state tomography. And how I already mentioned, this method reconstructs the complete density matrix of the emitted state by measuring the IQ, in phase, and the quadratic components of the microwave fields. To achieve accurate measurement, the heterodyne detection chain required exceptional stability, which was provided by a PID feedbacks. There are PID means um, uh, oh, we mentioned this is as there. Oh, so, ah, Purcell filter here. Yeah. So PID is a pulsar filter. Detect the feedback controller that continuously stabilizes the Josephson parametric amplifier. gain. With this setup, the amplification remains stable within 0.05 decibel during the hours long date accurating necessary for tomography. If you look this the uh, figures, there are the authors prepared the qubit in six different initial states. That's the ground, excited second, and the four equal superpositional, such as the shown. And each of these map to a corresponding photon states in the single photon substance. They record that the emitted field quadratic using the um, Josephson parametric amplifier and the reconstructed density metric of the photons. The average state fidelity was around 95%, and the process fidelity was measured the overall mapping from qubit to photon was similar. These numbers prove that the shaping and the turning process perceive a quantum coherence. The photons is not just classical radiation; it's a genuine quantum carriers. Now let's talk about why this matters beyond one devices. In real fabrication, each qubit and resonators end up with a slightly different frequency because of nanofabrication's tolerances, usually variations of a few ten of megahertz. If every node can tune its emitted photon over about for 40 megahertz simply by adjusting its drive, and any two nodes can find overlap and communicate. And the authors modeled this satisfactorily. If resonate the frequency have a Gaussian separate with standard deviation, were shown that's the 5 megahertz, and the each node has a tuning range 40 megahertz, then the probability that n number of the nodes not pairs can all be matched by this equation. This remains high above, even for around 10 pairs of nodes. So the demonstrated tuning range is practically sufficient for small quantum network, and because it uses only electronic microwave control, it eliminated extra flags lines and the magnetic noise. Even the result was so perfect they have, how we already mentioned, there are uh, 95 of average state fidelity was 95%, but there was also the limitation. Even so the first the system relies on the assumption that the resonators act purely as a Lorentzian bandpass filter. In reality, the transmissions line under the Purcell filter adds small phase delays and the reflections that slightly destroys the pattern involved. And these imperfections can be minimalized by calibration that output chain more carefully or using the impedance matched filters. And secondly, the shaping release on the adiabatic approximation, meaning that the drive amplitude must vary slowly enough for the system to stay in the instantaneous rest state. But for the quick shape photons too quickly, the qubit resonator energy exchange became non-adiabatic. And this sets a natural speed limit. So if they can emit photons faster than the system's coupling rate. So, and thirdly, the maintaining of stable phase over long experiment is challenging. Even with phase correction that they did, the local oscillator drift in the microwave electronics, and the noise of the amplifier can gradually degrade symmetrically for this reason. So for this reason, many laboratories use active feedback loops or reference tones to stabilize phase coherence. And the last, they also used in experiments um, Joseph, single Josephson parametric amplifier, which as the first stage amplifier, it can only record only quadratic at the time. So we say that we have two type of signals, that's in phase and quadratic. So this can record only the quadratic at a time. And the future properties of this experiment, the same techniques could be extended in several interesting ways. Using multimode resonators or engineered filters, banks might prove even lowered frequency tunable or enable frequency multiplexed emission. And combining this approach with microwave to optical converters could bridge superconducting processes and photonic communication channels. And another one, that's the develop real-time self-calibration where the system measures its own emission characteristics and automatically adjust the drive. The experiment could explore two photon or entanglement photon generation using similar of resonant control techniques. So to control this, to conclude this, to summarize, we can conclude that frequency tunable photons generation, single microwave photons were continuously tuned over a 40 megahertz range using only off-resonant drive without any flux bias, and the high temporal symmetry phase precompensation techniques improved waveform symmetry to over 98%, enabling nearly perfect time reservoir properties. And a high quantum fidelity, reconstructed density matrices show an average single photon fidelity of 95%, closely matching ideal quantum states. And firstly, that's the robust fixed frequency qubit platform, eliminating flux-based circuitry reduce noise, power dissipation, and fabrication complexity while maintaining precise photon control. And the last conclusion that we can do, that stability for quantum networks, the approach support modular uh, architecture and multi-node synchronization, providing a practical foundation for quantum communication and for the future quantum internet. So
Okay.
that's all. Thank you for your attention. And also, I
Mhm.
want to
Tell me.
that's about the journal,
Yes.
PRX Quantum Journal. It's about the quantum electronics, quantum optic, quantum internet. So which is integrated with the physics chapter quantum mechanics with the uh, microelectronics and so on other subjects. So thank you. If you have question, you can ask.
Okay. Okay. Somebody raising her hand, other hand. Okay, go ahead with the question.
So I have one question. My question is, you said off-resonant driving allow photon frequency tuning events of the qubit frequency is fixed. And my question is, why does off-resonant driving allow photon frequency tuning events of the qubit frequency is fixed?
Thank you for your question. Because of resonant driving creates dressed states of the qubit. Dressed states when there's a lot of states comes together. Slightly shifting its energy levels show the AC Stark effect. This shift causing the effective transition energy between the qubit and the resonator. So the photon is emitted at a frequency determining by the drive, determining not the barrier qubit frequency.
Okay, thank you.
So that's
Okay, thank you. Write your name, please, on the WhatsApp. Next one, if there is on more questions.
Um, so I thank you for this article presentation. It was really informative. You said that during the experiment they do the phase corrections, and my question is why it is necessary, and what physical effect caused the phase distortion that you mentioned.
thank you. How also I show the graph was differently, yeah? The before the phase correction. Where is? Oh, yeah. So the strong of resonant microwave drive included time-dependent Stark shift, which changed the qubit phase as the drive amplitude varies. This introduced a slowly drifting phase in the emitted Farron's field. Phase correction compensation for that by digitally adjusting the drive waveform to keep the photons symmetrically. And there are the all I mentioned this is all time, but I didn't give the definition for this AC Stark shift correction. So the AC Stark shift, this is the change in an atom's energy levels caused by oscillating electric fields like one from a laser. So that's all that as a depending of this
Oh,
Stark
okay.
shift. So here we do phase correction.
Thank you.
Okay, nice. Okay, I think that it has been a long time. We have a very long session today, and it is time to stop. And we are going to meet us next week with the next students. Okay?
Okay.
Yeah. Please send us. Don't forget to send us your link of the video. Okay. And see you next week. Okay. Goodbye to everybody.
Goodbye.
Bye.
Goodbye.
Goodbye. Goodbye.